In this video, we will introduce our work, AZ-NAS, Assembling Zero-Cost Proxies for Network Architecture Search. Network Architecture Search, dubbed NAS, aims to find a top-performing architecture under a specific hardware constraint, such as flops or memory budgets. We can design various search spaces based upon the purpose, which may include architectures with different operations, topologies, widths, or depths. Recently, training-free NAS has gained significant attention due to its efficiency. It predicts a performance ranking of candidate networks without training. To this end, the candidate networks are evaluated with a zero-cost proxy that captures a particular characteristic of a network. However, previous training-free NAS methods have several issues. First, they typically assess networks with a single zero-cost proxy only, preventing a comprehensive evaluation of networks from various perspectives. As a result, training-free NAS methods often provide less reliable results and are outperformed by training-based ones. Second, several zero-cost proxies are computationally demanding or require specific conditions for usage. This makes them impractical for use across various search spaces. Third, many zero-cost proxies produce similar ranking estimations, lacking complementary features. This could be problematic when we want to improve the NAS performance by integrating the predictions from multiple proxies. We believe that the performance of training-free NAS can be improved by designing new zero-cost proxies that complement to each other and assembling them with an effective aggregation method. Therefore, we develop a novel set of zero-cost proxies that analyze features and their gradients obtained from primary blocks. Here, we define a primary block as a repetitive structure that may contain multiple layers, operations, or paths. For example, we treat the cell structure of NAS Bench 201 or the bottleneck block of ResNet as a primary block. Now we will introduce our zero-cost proxies that are developed in terms of expressivity, progressivity, trainability, and complexity. First, the expressivity proxy checks whether all the channel dimensions of features are effectively utilized. To this end, it evaluates how features are isotropically distributed within a feature space, using the entropy of the coefficients of principal components. In this way, we can penalize networks having many dead neurons or suffering from a dimensional collapse problem. Second, the progressivity proxy evaluates an ability to expand a feature space along primary blocks, favoring networks whose features in deeper layers have more capacity to capture high-level semantic. The progressivity score is defined by block-level expressivity scores, ensuring that the block-level expressivity increases by at least the value of the progressivity score. Third, the trainability proxy checks for exploding or vanishing gradients during backpropagation. If a spectral norm of Jacobian for each primary block is close to 1, the backpropagation step becomes stable. Therefore, the trainability proxy assigns a high score when the spectral norms from all primary blocks are close to 1. Lastly, required hardware resources of a network, such as flops, show a good correlation with a performance ranking. We thus set the complexity score based on the flops count, favoring networks that maximally use computational resources within a given budget. To effectively aggregate the aforementioned proxies, we propose a nonlinear ranking aggregation method. It penalizes a network more significantly when a particular proxy indicates subpar performance, prioritizing networks that exhibit high scores evenly across all proxies. We evaluate our approach on NAS Bench 201. In the left figures, we can see that each of the ranking predictions of our zero-cost proxies in the x-axis shows positive correlations with the ground truth performance ranking in the y-axis. By assembling them, we can improve the ranking consistency drastically, and our nonlinear ranking aggregation method performs more effectively. We also compare our method with the state-of-the-art in the right figure. AZ-NAS outperforms others, while retaining the efficiency of the NAS process. We also perform experiments on the large-scale MobileNet search space. The results demonstrate that AZ-NAS provides reliable and best NAS results consistently across different flops budgets. For more results and information, please see out paper. Thank you for listening.